Welcome back to the database seminar. Today, it's a pleasure to introduce Chunbin Lin. He's one of our own alumni from the CSE database lab. And Chunbin worked with Professor Yanis Papakonstantinou. He graduated 4 years ago and joined Redshift at AWS. And he's back here to tell us about autonomics in Amazon Redshift. So a little bit of protocol. Chunbin, do you want questions during, at the end, both?
Yeah, either way is fine.
Either way is fine. Okay, great. So students, please feel free to post questions on the chat, or Chunbin can pause in between and take questions as well. And otherwise, we'll get started. So Chunbin, all yours. Okay.
Thanks a lot for your introduction. And I'm really happy to be back in UCSD database seminar. It has been 4 years. And today I'm going to present autonomics in Redshift. Okay. So, yep. So Redshift is a data warehouse, and it has most customers, over tens of thousands of customers that process exabytes of data per day in Redshift. And for the use cases involving hundreds of terabyte data or more, Redshift is proven solution for analytics at scale. And it has many features actually. From the high level, it has best performance. So Redshift has the world's fastest performance, because we continuously improve the performance by adding more and more optimizations by using for example, machine learning algorithms and the CMD, some hardware optimizations. And Redshift also have a hybrid storage strategy. That is, it can process the data in S3, and also it can it has in-class data storage. And this gives us different functionalities, right? So for data in S3, and we are able to, for example, scale the data, and for data in on instance, we are able to process the data in a very high performance, and it can be achieved in any other way. So our unique combination of these two different storage strategies actually makes Redshift has the best in-class performance today, and also leaves room for the performance improvement tomorrow. Okay. And yeah. So as I mentioned, Redshift can scale very well, and it scales from 128 gigabyte to 8 terabyte, and there's no limit on how often or how much you want to scale. And as long as, for example, your workload has increased concurrency request, and then we just add concurrent scaling cluster to process your data. I will introduce later in the details. And also Redshift integrate with AWS environment, so for your data lake, and you don't need to re-architecture your cluster. You can access any kind of data in S3 data lake, which means you can process your data sharing or data lake, real-time analytics, ML, AI workload using Redshift. Okay. And the Redshift has another feature, advanced feature, that is it is really easy for use. So you don't need to worry about what kind of distribution keys or short keys you need to specify, and Redshift take care of everything. Everything now is automatic in Redshift. We have automatic distribution key recommendation, automatic workload management, and also automatic materialized view rewrite. And I will introduce all those details later. And for security, AWS already provides a very comprehensive security compatibility, and the Redshift actually on top of AWS provides a better security, because it provides different layers of security, and the customers can safely ingest their data to Redshift and query there. And in terms of cost, actually, Redshift has a very, very low cost, and it only charge for like the data you used, and yeah, customer really like this low cost. Okay, so those are the high level features of Redshift. Now I would like to dive deeper into Redshift architecture. So when we go back to 2013, and the Redshift is as easy as you see, like one single node and then multi-compute node, that's it. And till last year, we add a lot of components to Redshift. For example, we have a concurrent scaling cluster, and we can process streaming data. And also we can write like a machine learning model in SQL in Redshift. For example, you can create model in Redshift, and then we will send the command to SageMaker actually to create machine learning models in SageMaker or in other different places, and then reference those machine learning model also in SQL. And also in hardware side, we have a lot of like hardware optimizations there. And we can also process different type of data now, for example, like Parquet, ORC, JSON. So we add more and more functionalities, and also we improve the performance every year. So in terms of the price and the performance, you can see Redshift achieves the highest price performance here compared with different computers. Okay, no matter it is out-of-box workload or it is tuned workload, Redshift has the best price and performance. And also, when we look into the short queries, for example, dashboard queries, right? And the customers care about the throughput of those short queries. And Redshift has optimizations to speed up the short query throughput and the performance of the short query. And you can see from here, like when we increase the number of streams in the workload, the short query throughput actually is very high in Redshift compared with the other database. And the one interesting feature in Redshift is like it can provide a linear scaling performance. That is, no matter how big is your data, for example, it is 10 terabyte or 30 terabyte or 100 terabyte or even 1 megabyte. That's fine. Like the performance is very stable. Okay. Yeah. So we previewed some features in Redshift and also previewed some like performance data, price performance data there, and we know like Redshift can achieve high performance. But how Redshift achieve this high performance actually? One important feature is Redshift use machine learning algorithms in many different areas. So for example, we use machine learning in operations, and we can automate operations in, let's say, 84 different availability zones. And we don't need to care about like whether cluster is down or hardware has errors. Like we have machine learning to detect this error, and then can generate the logs. And then for the operation on call, people can directly jump into the issues there, and it will be very easy. And also we use machine learning to manage resources. For example, when queries with different resources, and then we just assign the right amount of resource to the query. And yeah, I will also introduce the details later. And yeah, let me skip this one. So this one, yeah, has the covers actually most of the features in Redshift with automatic. So in Redshift, we provide like automatic in many different areas, as I just mentioned. For example, we automatic table optimization. That is, we can automatically generate this sort or distribution keys based on your data and also the workload type. And we keep optimizing your table actually. And I have another figure to show, like after you load your data and with the hours like going up, you can see like the performance improved by Redshift automatically optimize your table. And also we also have like auto analyze, that is like we analyze to generate, let's say, cardinality or something. So everything is automatic there. And the one important feature is automatic materialized views. I will also introduce later in details. That is when we create the materialized views and then we detect you have workload change, and we will automatically like rewrite these materialized views. And yeah, those are the automatic in database tuning. So yeah, this figure shows like when you load your data set to Redshift and with the hours increased, and we apply this automatic algorithm to your tables, and then it will like suggest the right distribution keys or shortkeys in your table, and then we apply this distribution keys there, and then you can see like with this applied distribution keys, and then when you rerun the queries, and then the performance improved a lot. And the last year, we also announced a new feature called automated materialized views. So materialized views are like database object that contains the results of the proposed results, and the Redshift provide automatic materialized views. It can automatically create and delete materialized views based on like the workload change. For example, if it can detect, okay, now if we create a materialized view, and then the future query can reuse this materialized view, and then the performance will like speed up the most, then we will automatically create this materialized view, and the users doesn't need to specify this materialized view manually. And of course, we also provide a way like to manually create and manually delete materialized views, but in order to achieve the highest throughput, and everything now is automatic. And we know, like, for example, if we drop and then recreate a materialized view, for example, it might take 1 minute, but if we incrementally refresh this materialized view, it only take 1 second, then we will suggest to incrementally refresh the materialized view. Okay. And then the last one is called automatic workload management. And then this is also the part I would like to focus on in today's talk. Because workload management in Redshift is the most important components, because all the queries, if you want to be executed in Redshift, it needs to go to workload management first. So workload management need to assign resources to queries. For example, need to assign the CPU memory to the query, and also need to control the number of queries can be admitted into the system. For example, like if you have 5 non-running query submitted to the to Redshift, and we might admit only, let's say, 4 of them, because 4 of them already used all the memory, right? But if you have like 100 short queries coming at the same time, and we will like automatically increase the concurrency to admit this 100 query into the system directly, because short queries usually use like less resources than non-running query. But it's not like this easy, right? It depends on the we use machine learning algorithm to predict these resources required for each query, and then we have algorithm to control the number of queries can be admitted into the system. Okay, and once we like figure out.
May I interrupt with a question?
Yeah.
Are you going to tell us a bit later how you cost these queries in order to identify which of them are short, which of them take a lot of memory, and so on? Or is this not really the focus of the talk?
Yeah, it is the focus of this talk.
Okay.
So yeah, I will
You get that?
Okay, yeah, this is one of the challenge actually I'm going to say. And because, as I mentioned, like one of the goal is to improve the short queries response time. But in the very beginning, we need to identify like which query is a short query or not, right?
Exactly.
Correct. Yeah.
Okay, cool. I'll wait until you get there. Thank you.
Okay. So now I just give a very high level like summary of how workload management works in Redshift. Okay. So we have machine learning model to predict the resources of queries, and then we check whether we still have enough like a resource for the query. If yes, then we admit the query into the system. But notice that the machine learning model might give non-prediction, right? Because the prediction quality is not 100%. And we have like feedback loop to monitor the current system utilization. For example, if we detect that now we have too many queries admitted into the system, then we need to lower the concurrency because we already overuse the system, okay? And similarly, like if the feedback loop detect we are underusing the system utilization, then we should increase the concurrency to admit like more queries into the system. So this is the concurrency control I will also mention later. And then the last important components in the automatic workload management is we call it the priority. Because when customers submit queries into the Redshift, each query comes from different user group and may have different priorities. Okay, basically like different job have different priority. For example, ETL job might have higher priority than some analytics job, and we don't want to block, let's say, high priority queries by low priority queries. But at the same time, we don't want the low priority query to stuck there forever, right? Even it is a low priority query, we still want it to make progress instead of stuck there, let's say, for one day. So in order to like address these challenges and then also to provide the optimal concurrency control, and we spend a lot of time in workload management in Redshift. Yeah. So here's the history of the workload management in Redshift. Before 2017, and we only have manual WM, or called manual workload management. So customers need to define concurrency memory for each queue. Queue means like, for example, we partition the resources in Redshift in different queues, and customer need to define like how much memory, let's say 20% memory assigned to each queue. And yeah, so everything is manual. Users need to identify the right concurrency, right memory. And that is before 2017 and before I joined actually. And later we have one important feature called short query acceleration, or short for SQA. So that is just to improve the throughput for short query. But later we observed that like this feature is not enough because users submit more and more queries to Redshift, even though we have this short query optimization, but we also want to like optimize the overall throughput for the whole workload, not just for short query, right? So we introduce concurrent scaling, which means like we can scale out when we have, for example, like 1,000 queries submitted to Redshift, but Redshift can only handle, let's say, 100 queries at the same time. And for the other 900 queries might be queued there. So instead of queuing the queries in Redshift, we acquire another concurrent scaling cluster, and we send the queries to those clusters to execute and then send a result back. So all the queries can be executed dependently, okay? And after this feature, we figure out that we still have limitations because the concurrency the workloads keep changing, and we need to predict execution time of each query and the memory, CPU, and with this predict information. And we now know whether like we have enough resource to admit this query or not. And if yes, then we admit into the system. Okay, so we call this one auto WM. Okay, and I will introduce each one in details. So in the very beginning, as I mentioned, we have this manual WM, and the users can create the queues. Queues means, so for example, you have a ETL queue, and with user group ETL, and all queries like under this user or maybe this user group goes to this queue. And then the challenge is the user need to specify the number of the percentage of memory and also the concurrency on each queue. For example, like some customers set 82% memory for this queue, and another 18% of memory for, let's say, monitoring queue or something. And also is need to specify the concurrency on this queue, let's say 15. 15 means like we can process 15 queries at most, okay? And it is good for simple fixed workload if we know like every time we have 15 queries submitted to the system, and those queries will use, let's say, 28% of the memory, then it is perfect, right? But however, like workload keep changing, and also you can see in this figure we plot here, like the query latency is totally different. It changes all the time, and also query arrival, number of queries arrival also changes all the time. For example, at this time, let's say 8 a.m. and when people start their business, and then you might see like 200 of dashboard queries submitted to Redshift, right? And during the night, there might only have some ETL queries running, maybe only 6 to 5 queries. So if we have fixed memory or fixed concurrency, so it has a lot of limitations, like it wastes the resources, because when the queues are idle, and then the resources are already reserved to that queue, and it cannot be used in other. And also, the concurrency, for example, you set to 15, but only 3 queries are submitted to the Redshift, so you waste like all the resources there. And the most important is like short queries are blocked by non-running query because there's no mechanism to prioritize these short queries, right? So in order to prioritize short queries, one feature is called short query acceleration, or SQA. And we need to address 2 challenges here, because there are 2 different scenarios. Like the worst case is, for example, the short query, or for example, 1 second query, right? It might wait in the system for 1 minute or maybe 1 hour, and then it's queued. That is not a customer want. For example, 1 millisecond query, a dashboard query, we submit it, but there are already, let's say, 10 non-running query in the system. And then this short query might queue there because we don't have resource to execute this query. And it will wait there for 1 hour until the non-running query finish, and then we execute this 1 second query. And then the user experience will be terrible. This is challenge 1, and when like a non-running query occupied all the resources, and the short query has no chance to execute. Another challenge is like some short queries are running, but some short queries are queued behind non-running query. So there are some non-running query also queued there, and the short query also queued behind non-running query. And then you need to wait until this short non-running query is executed and finished, and then you have chance to execute this short query, right? So we need to address these 2 scenarios which blocks the short query to be executed. But before that, we need to identify like what kind of query is short, and how to identify like whether the query is short or not, because we don't know. when you submit a SQL query, we only know this SQL text, select the stuff from something, right? Okay, so in order to address the first challenge, that is like a short query wait there while long running queries are running. So we need to dedicate the resources for short query. Basically, we need to reserve some memory for short query. But short query only use very little memory, so we only reserve, let's say, 5% of the total memory for short query. And for this, the second challenge, that is like short query queued behind non-running queued query. So we need to figure out a mechanism to prioritize this short query in the waiting queue. That is, we need to send this short query to other queue to execute instead of like wait together with the non-running query in the same queue. And in order to find which query is short or not, basically we have a machine learning model to predict whether a query is short or not. And if, I mean, as I said, then the prediction model might not be 100% accurate, right? So we have a timeout there. So for example, we identify that this query is short and then the execution time is less than 10 seconds, but actually it takes 30 seconds. That is fine. We identify this query as a short query, so we send this query to the reserve the queue to execute. But after 10 seconds, we figure out, okay, you are not a short query. So there are two options in Redshift. One is to abort this query and then restart it. Another one is to hop this query back to the user queue and keep executing. And we won't like waste 10 seconds there, right? And then these two options are all applied in today's Redshift because some of the queries cannot be hopped. For example, some DML queries, so we have to abort and then re-execute. And yeah. So one coming question is, okay, so how we use machine learning in database to predict? Because we only have SQL text, right? And in Redshift, actually, we when we submit the SQL text to Redshift, we pass the SQL to pass tree, and then plan it convert to planning tree, and then we use this plan tree and convert to like features, for example, the cardinality, and use this one as input. Basically, for each query, we use the plan tree as input of the machine learning model, and then give me prediction. Okay, so for a new coming query, we again we do the parsing and the planning, and again the plan tree, and then fit into the machine learning model to get the output of the execution time. And here is the graph of the accuracy of our prediction model in product. Okay, so
may I interrupt before we look at its efficiency?
Yeah.
So when you say you plan, is the plan cost-based?
Is the plan cost-based?
Yes, the plan that you obtain from the syntax of the query, is that one cost-based?
Yes, it is.
Okay, so we have here a cost,
Yeah,
which is probably rather traditional and is not based on on learning, right? And then you take the input of the costs into the plan, you take the plan, and that one you learn from. Do I understand this right? Is there any connection between the cost model that you apply for planning purposes and the machine learning for trying to cost after the fact, whether you're qualitatively at least you are costing, you are deciding that this is a short query?
Yeah, so actually these are two orthogonal questions. So we do have a project to use machine learning model to predict like which plan is the best one. For example, like we predict the join order, okay? And here actually what we decide is like you already finished the plan and we need to execute the query. So basically we need to choose which query needs to be executed now. So for example, it is not a single query, right? You submit, let's say 10 queries into the system, and after planning, and we identified like this query with this plan, it will be a short query, right? So we will execute this short query first.
I get that. I'm just wondering whether there is some sort of feedback loop here between the cost model, which does not seem to use any learning, and the classification, which is learning based.
Oh yeah, I got it. Yeah. So this is actually one of our coming feature, that is to provide this feedback loop in planning. And because now like the machine learning model in
Unless I do something about it, I could have a cost that is rather low for a particular query, and I would come up with a plan, which then your machine learning classifier classifies it as long. Can that happen? And if so, how is this fixed automatically?
sorry, your volume is very low, but I think I got your question. So you are asking like, because for this plan, we already paid the cost, and then how do we actually address this issue, right?
So Chunbin, I think Alan's question was, when you're doing the query planning, your cost model gives you an estimate potentially of the execution time already. So this physical plan that you obtained already included an estimation of the runtime using the analytical cost models. So the question is, why can't you just reuse that from the analytical cost model estimates to just say, is it long running or short running? Why do we need a separate machine learning model on top of that?
Yeah. Okay, got it. So this model not only gives the execution time prediction, but also gives the memory and the CPU prediction. Okay, so this is one thing. Yeah.
So you wanted a unified machine learning model to do time and resource utilization predictions, whereas your analytical cost model for query planning only does time.
Correct. Yeah. And there's another feature actually now we are working on, that is AI will introduce later. Actually, it is in the second slide. Before I jump into the second slide, let's preview this accuracy of the. As I mentioned, that we are not only predict time, right? So we also predict memory and the CPU. The CPU we just released actually this month, and we haven't gotten the free data from the product. So now we only have time and the memory prediction, and then the time prediction accuracy is, and both time memory accuracy is over like 97% for short query. For non-running query, we do have like low accuracy, that is, let's say 85%. And that is why we add like feedback loop in workload management to avoid this bad prediction. Okay. And yeah, now the follow-up question is like how we train this machine learning model. So we have machine learning model per cluster, and so for each cluster we have the machine learning model, because like it only got trained by this workload running on this cluster. And every like hundreds of queries finished, we retrain the machine learning model. And another project in Redshift is to have a global machine learning model outside like all the clusters. So the advantage there is like it can use all the data across all the clusters. And even with a new cluster, so for example, you just create a new cluster, and we can directly use this global machine learning model to give the prediction, right? And once you already have some queries running on the cluster, and then we can gather more information from this particular cluster, and we can have like better prediction model on each cluster. But so far in Redshift, we only have local prediction model. That is, for each cluster, it has its own machine learning model. So because the motivation is like different cluster have different workload, and each cluster uses its own machine learning model to give prediction, right? But then last year, actually, we did some experiment. If we have global machine learning model, it can see like more data actually, and it has opportunity to have higher accuracy on prediction. But we are still that one is still ongoing. So far, we have only local cluster machine learning model, and it got retrained every 200 to 200 queries. So when we finish like 200 queries, and then we refresh the model. Yeah. So here is the summarize of this short query accelerator called SQA. So for example, like these colored box are queues. For example, we have ETL queue, analytic queue, and the circles here are queries. Okay, so the blue color circles are queries already running in the system, because in this example, like ETL queue can handle 15 concurrent queries. So there are 15 queries running, and only white circle means like queued queries. So you can see there are some short running queries, 3 seconds, 1 second queued there, and also long running queries, 300 second, 550 second queued there. And what SQA does is to pick this short query and route the name into a reserved short query queue, and it's queued there. Okay, so it doesn't need to interact with this non-running query, and just execute on a separate queue. So we get like many benefit by doing this, and this is the result. For example, from the baseline is the well-tuned workload management, and then the green one is the one like without using the prediction. That is, we treat everything as short query. That is, we send all the query to SQA. Because in SQA we have timeout, and then if it is really a short query, yeah, it will finish there. Otherwise, we will timeout and then send back to the user queue. Okay. And the red one is today's Redshift. That is, use this SQA with prediction, and you can see like execution time is better than without prediction. And another challenge is, let's revisit this architecture of Redshift. And one feature is like when we don't have enough capacity in the main cluster, we add another concurrent scaling cluster to handle like more queries. So let's go back to this example, okay? And now we have like SQA to speed up short running query, but we still have long running query queued there, right? And do we want to like wait those queries there until all executing queries to finish and then start executing them? Or another choice is to send those queries to another cluster to execute on concurrent scaling cluster and then send the result back, okay? But concurrent scaling cluster in Redshift is not free. We offer like a 1 hour free concurrent scaling cluster per day to customers. And if it's more than 1 hour, the customer need to pay the cost. So with concurrent scaling, actually the throughput is linearly increased when we have increasement on the concurrent user. So if you have, let's say, 200 concurrent users, then you will have higher throughput by adding more and more concurrent scaling cluster into Redshift. And yeah, so, but we know like there are a lot of limitations in manual WM, because you need to specify the concurrency memory and used in each queue. And in order to like provide ease of use feature, so we remove everything. So now everything is auto, but customers need to define priority. Priority is not necessary if customers don't define the priority. Internally, like in the system, we will automatically assign some priority actually we want to assign high priority for short query. But if users specify the priority, then we will use this priority defined by customers. Okay. And the AutoWM does several things. One is to assign the resources to queries. Another one is to control the concurrency. And the third one is to use priority to determine the execution order. And we can see here, like with different concurrency, and we have different performance. Okay, that is why we need to control the concurrency. So, for example, this is the query. This is the query arrival time. And in manual WM, let's say if we set concurrency to 15, and for the other queries, for example, like 20 queries will be queued there because you only set concurrent to 15. This is the fixed number in manual WM, right? But if you, in order to handle the peak, you set concurrency to high, let's say to 25, and most of the time you just underuse the resource because you only have 3 to 5 queries running there. So it doesn't make sense. And in automatic workload management, or we call it AutoWM, it dynamically controls the concurrency that is based on the number of queries in the system, and it adjusts this concurrency to fit like to set the best concurrency in order to maximize the throughput. So in Redshift, actually, we use machine learning model, as I just mentioned, to predict time, memory, and the CPU. Those are 3 factors we predict. And we prioritize like short queries because we already know like those queries are short query, and we send the short query to a short query queue. And we have feedback loop if we have wrong prediction. Okay, so for example, like we predict the memory for a query to 1 GB, but actually the query only needs 1 MB. Yeah, it doesn't happen very frequently, but it happens sometimes. And we admit this query into the system, but then we figure out, okay, queries start speeding to the disk. And in the feedback loop, we detect this, and then we lower the concurrency to allow like a few less query into the system in the next time window. So this is how we adjust this concurrency. And we also mentioned like in Redshift that we have concurrent scaling feature to scale out. But concurrent scaling is not free, right? It is expensive. So we also like provide query priority, because customers only cares about like high priority queries to finish first. And if we can prioritize like high priority queries and then make sure non-running low priority queries can also make progress, and then they can finish in one cluster actually. And the idea is to provide a starvation control for low priority query by using weighted round robin algorithm. That is, we always give some chance for low priority query to run. Let's say after we execute 10 high priority query, then we pick 1 low priority query to execute. And we have like a dismission control, as I mentioned. So we can make sure like the most important jobs can finish faster. Yeah, I already mentioned like we have different layers of starvation control, like in the IO layer and the CPU layer. So when we have defined the priority, you can see like highest priority has highest throughput, and because it has like a lowest queue time, because we admit high priority queries to the system first, right? And for low priority query, it won't stuck there forever, so it has longer queue time, but it can still finish in time actually. And then this is the details of like before and after applying this priority to the system, and you can see the response time changes. And basically, after applying priority, short query get a better response time compared to long running query. And the customer really like this feature. And also we have a lot of experiment compared with auto WM to manual WM. Manual WM means some very experienced DBA, they tuned their workload management to have the best config. And even compared with the best config, and auto WM actually does better, because even with the best config, like when you have spike in the workload, and manual WM cannot adjust the concurrency, right? But auto WM can adjust the concurrency dynamically, so it has like a better response time. Okay, so for workload management, and the summary is Amazon Redshift, they use machine learning to predict the execution time, memory, CPU, and adjust the concurrency and memory like dynamically, and schedule shorter query ahead of longer query. So when we plus all of them together, we get better throughput and better like user experience. This is the summary for workload management. But okay, now the summary for the whole Redshift is like we can we process tens of thousands of customer queries per day on actual bytes of data. And we actually have integrated with like all the AWS environment. And also we apply the machine learning in Redshift everywhere. We automate all the features in Redshift. And yeah, we have like office in different places, and we are still hiring. Okay, that's it. Any questions?
Great, thank you, Chunbin. Let's give Chunbin a round of applause. So we do it virtually. I don't see a clap, so I'm going to give you a coffee mug.
Okay, cool. I'm on time, right?
You're on time.
So we still.
You have 10 minutes for questions. Audience questions.
Chunbin, I have a question. So Redshift is meant to be a highly heterogeneous data store, right? You were mentioning JSON and other data formats.
Right.
And in order to learn, you are looking at plans.
Mm-hmm.
So my question is, do you have some sort of universal plan algebra that you're using across models? How does this work?
So, okay, so your question is like we process heterogeneous data, and do we have like models to distinguish this data type, right?
Yeah, and in particular, given that plans are inputs to the machine learning classification.
Correct.
You need some sort of universal plan notation that would go across data models. And have you designed something like that? Are these results that you're showing here only limited to relational data sub?
No, it's not restricted to relational. Actually, it is for all the queries, and because for the plan in Redshift, we do know like it is which type of queries and which type of data you touched, right? And those features are also used when we train the machine learning model.
Right, but before we even get to training, so you have an algebra of operators that allows one to express plans that reach across data models and that join data from different containers that each are satisfying different data formats and so on. Is there a universal language here for plan?
No universal language as far as I know, actually.
So my guess is they just have physical operators for the different file formats.
Correct.
Parquet, Arc, Avro, they're all file formats to just store tables. My understanding is JSON is also a file format for storing tables. Correct. Or semi-structured data, but they're physical operators at the lowest level when they're doing the scan. They just convert that to the relational abstraction for subsequent processing, right?
Correct. Yeah, it's
So
not.
so for all data models, are you using the relational model as an intermediate data model to convert everything into for the purpose of your execution? Is that what happens?
No, it's not like that. For example, like for different type, actually we have different optimizations in the execution level, but in the planning level, actually, we don't distinguish those actually.
So like, for example, there is no JSON querying integrated with Redshift, right?
Yeah.
The JSON file format is used to store relations, not semi-structured queries. You're not handling graph structured queries or anything like that. Got it.
No.
Okay.
So it's really just a
So
file
then
format support. Yeah.
Yep.
Okay. So it's really the logical data model that is manipulated by your operators is pure relational, and there are some wrappers that pull from some other data format into tuples, and from then on, these tuples are just fed into the rest of the operator tree.
Correct. Yep.
That's correct.
Yep.
Okay. Okay. Thank you. I get it now.
Okay. Cool.
Have a question you have?
Hi, Chunbin. Thanks for the brilliant talk. I'm very curious about Redshift. I have a question about the so on this slide I also mentioned the integration with the entire AWS environment. So I'm wondering how does Redshift work with other AWS resources like EC2, EMR, or even the Lambda functions? Do you have to like pull out the data into some other resources, computational resources?
No, we don't need to pull up data actually, because we already have like project to grant the permission from them, and you can directly like submit the query in Redshift and then query the data from their side. So basically, like you can push some operations, let's say, to different AWS components, and then when you like get the result from them, and then you can keep processing.
I see. In that case, so I'm even more curious about the storage layer of the Redshift. So, what kind of like file formats if you are like trying to manage the data? Can other resources directly access the same set of data format? I'm asking because there's this new envision stuff called Lakehouse that proposes to use universal data formats, universal data files that can be shared across the data warehouses and also the other machine learning platforms. I'm wondering if that's the thing that you are already doing right now.
No, we are now still focused on like Parquet, and as I mentioned in the architecture, right, those like 4 different formats we are focused on now in this architecture figure. Oh, sorry, it is very small. So like JSON and ORC Parquet, I mean, those are like a widely used format in S3. So yeah.
So my understanding is the managed storage is where you store the files in your own format for optimized scans, whereas the open file formats that are stored in S3 are your lake component, correct?
Yes, correct. Yep.
Got it.
And for our own like storage in Redshift, and it has like a metadata like on top of it. For example, we have room filter, min max, and also some zoom maps there. And for these files stored in S3, actually, for example, for each partition, we also have min max, but we don't have like the other type of filter, for example, like a Bloom filters there. So we have basically have different metadata actually for local and this S3 data file format.
I see. So if I remember correctly, Redshift is this database as a service thing. So basically, the user has no access to the Redshift managed storage part, but they do have, they do have access to the S3, the external files. Is that correct?
Yeah, you can use like in Redshift. We have another feature called Spectrum, so you can directly access the S3 file by using like Redshift.
But
Cool.
if you want to access the managed storage files, that you have to go through the query stack of Redshift for
Yeah.
exported CSV, like a typical RDBMS. Right? Okay, cool.
Cool. Great. Thank you.
More questions from the audience? Yeah, I have a quick question about the generality of the models that you built for some of these. The featureization you're talking about is based on a query plan. Does it also take into account any information about the schema, about integrity constraints on the database and stuff like that? And if so,
Yeah,
how will
this
it
is a
be general as the
question,
database
actually.
evolves? What if people change the database schema? What if new tables are added, new columns are added? How general can these models be?
Yeah, so far like we only consider the pantry, but there's like ongoing project, as I mentioned, that we want to have like a global machine learning model outside. And the input that we also want to change to like not only pantry but also like schemas, and then as you mentioned. So this one has not released yet, and that is why I didn't mention it in the slides.
Okay, that's fine. Secret stuff.
Secret stuff.
Is there a benchmark for this kind of stuff yet? I mean, the TPC benchmarks, TPC DS.
Yeah. For like everything in my slides, we have benchmark here.
Okay. Cool. More questions from the audience? If not, I'll have one last question, then we can wrap up. So increasingly with serverless operations, people are even like serverless query engines like Athena, people want to provision resources on demand, right? Not on demand, on the fly.
On the fly.
An AWS land is something else. You want to provision resources on the fly. Some of your concurrency cluster that you're talking about is actually provisioning resources elastically and then downscaling it. Do you see a future where Redshift will automatically allow that to happen for all kinds of queries, where you give SLAs on the latency and then you can auto scale up and down? Or do people still need to have provision storage?
No, I think in the future, people doesn't need to have provisions there. And what you just mentioned, it is the future actually. Because ideally, you don't need to have anything, right? It will just like scale down or scale up automatically.
And so that is part of the plan for the future of Redshift? Yeah,
but not this year.
Not this year. Okay. I see you have auto scaling cluster there, so I assume that's what it means.
Right.
Okay, sounds good. That sounds exciting. I think you would need more machine learning for auto management of resources at that scale, at that level.
Yeah, actually, especially for like workload management, and we need a lot of machine learning people here. And yeah, for example, Marley is also working with us now.
Okay.
And we keep hiring like machine learning experts.
What sort of folks do you hire? Data scientists and then try to train them on the internals of your system architecture, or do you try to teach machine learning and data science to the RDBMS developers? Which way do you go?
This is a good question actually. We want to go like both ways.
Yeah, which is working out for you so far?
So far, like we hire machine learning like data scientist and then machine learning scientist, and then to like teach them actually how to use the pantry to get prediction, and then they figure out how to fit like more input to their models and then compare with their result to our baselines here.
Got it. Okay, sounds good. So that's sort of the high volume traffic coming out of academia. More data science students than students who understand internals of DBMS system implementation.
Correct.
Okay, sounds good. So I think we are out of time now. So thank you again, Chunbin.
Okay, thank you.
The audience for joining. And
thanks for coming, Chunbin.
Thank you, Ali. Bye-bye.
Everyone, I'll stop the recording here.